So thank you, Alex, for the introduction, and also thanks to Elias for the organizing this this seminar. So this talk is about a best submatrix selection, and we'll provide a new angle for this type of problem, and also derive some approximation algorithms. And this is joint work with my students, Yongchun. So a good motivation example for this type of problem is for the PMU sensor placement in power system. So in power system there are two types of sensors. The first one is a scatter, which has been used widely, but the new one, okay, it's not very relatively new. New one is called PMU, which is much faster and it's much faster and is much more accurate. But of course, we have to pay more for that in terms of installation fee and also labor fees for this type of sensors. And so the scale problem we are talking about is like, okay, we have like thousands of buses. So it's like each bus, we can install a PMU sensor there. And they might want to install, for example, if we cannot afford to install so many sensors to all the buses, but we might be able to install, for example, hundreds of them to different buses. Okay, so the question here is, how can we install those kind of PMU sensors to this type of power grid, such that we can maximize the information, collected information. So the basic assumptions which has been used by many literature is called that for the observations, they follow joint Gaussian distributions. Or alternatively, we can also further generalize this type of problem to, for example, they follow joint elliptical distributions, and we got a similar results, and it's just similar approach just works. Okay. So since we are talking about the maximizing information obtained by those buses or those sensors, so how can we measure the information? Fortunately, like many years ago, like almost more than 70 years ago, the Shannon they provide a nice formula to compute compute information called Shannon entropy. So it can be spread like this. So suppose we select a subset of buses or subset of sensors, and the Shannon entropy can be computed like a minus of expectation of log of this f is called probability density function. Okay? So this can be a very complicated formula because the expectation of high dimensional random variables is very difficult to evaluate even. But fortunately, if under this Gaussian distributions, we got the closed form expression. Okay? So this problem can be reduced to such kind of form where, so here we let C, the matrix C denotes the covariance matrix of entire observations. So this can be collected by the previous data, and so we know this one based on the historical data, the C covariance matrix. And the maximum entropy sampling problem can be formulated as follows. We maximize here. We maximize the entropy, but equivalently it can be formulated like we maximize the log determinants of a principal submatrix of covariance matrix. Okay. Here, S means a subset of buses, for example, and this is a subset, and the size of this S equal to small s. So entire problem, if we can be simplified as we are trying to choose. We are trying to choose a principal submatrix with size S from this covariance matrix, such that its log determinant or its value or the information can be maximized. So this type of problem, you can see from its description, can be very difficult problem, and has been studied by many researchers in many kind of different areas. And for example, in 1995, it's already been proven. So it's also not surprising results. It's an NPR problem. And the nice structure you might wondering is this formula. It's a submodular in terms of the subset S. So, but you should be careful here. The submodularity only holds when C, the covariance matrix, is a positive definite. Okay. So if the covariance matrix is a singular, then the submodularity does not hold. Okay. So which means if there are some two observations, they are kind of identical to each other. Then this covariance matrix is a singular. Then this submodularity does not hold. So should be careful. And the two properties which go against of this modularity so usually we don't have non-monotonicity, which means as S grows, the small s grows, the size of substep grows, the object function, the information, the maximized, the information log determinant might decrease. So it might not be monotonic, non-decreasing. Also, the object function can be negative. So why we care about these two properties? Because the well-known results from named Hauser and his collaborators like Woolsey and Fisher, they show that for the maximized monotonic and positive non-negative submodular function has very nice approximation guarantees. But for this type problem, to complete it, we might not have any of these satisfied. So the existing approximation ratios really cannot directly apply to those kind of problems. Okay. So that's also motivate us to develop some new approximation algorithms for this type of problem, which works well. And another one you might be curious is it's also very expensive to compute the determinants, which means if we have this log determinant function, so you know, if even we run the greedy algorithms to solve this problem at each iteration, when the number of sensor grows, the computing of the determinant takes a lot of time, because we have to compute this again and again, which is maybe not very desirable if you design a greedy algorithm to directly to solve a very large scale problem. Also, this also motivated us to find an alternative way to present this problem in a different angle. Okay. So several applications we want to mention here, for example, in social network. So those are all from literature. So for the social network, for example, we have billions of users in Facebook, and sometimes they want to sample some important entities from this, the most important entities from this, or most users, important users from the social network, so they can analyze this in a better way. So it's a sampling problem. Another one maybe worth to mention is, for example, even in stochastic programming, if we have a lot of samples or a lot of scenarios, how can we sample input? We can further reduce the size of stochastic programming without loss of too much accuracy. We can also sampling a lot of scenarios or samples based on this one. Based on this approach. Second example, for example, for the drug design, we know the clinical trial is very expensive. So, for example, in the another one is for the cancer treatment. There are, for example, breast cancer. There are more than like 27 drugs which are useful. So in this case, how do we choose a best combination of different types of drugs for the clinical trial, and only a very most important subset of drug combinations? It's a very important problem, and because you know the clinical trial can be expensive, and you know, and the time also limited. So it's interesting for us to select the most important combination of these different drugs for the testing purpose. And the last one, for example, even this type of method can be applied for the hyperparameter tuning problem. So, you know, the recent work show that the deep learning really works very well for image processing problems, image data. But the neural networks, if you know, if you use this as a lot of available packages, the tons of parameters need to be tuned before we use it, before it works very well for the particular problem. So when we see this kind of problems, for example, how many layers do we need, and even what kind of optimizer we want to choose for deep learning, that's also a question. You know, if we just simply enumerate all the possible parameters, it can cost a lot of time to tune this deep neural networks. Okay. So the hyperparameter selection. So we choose. We have different type of hyperparameters, and we choose the best combination of hyperparameters, which can save a lot of computational time, and also, you know, can also train also on the same time. We still train the model very well. Okay. So hope you have some sense about this problem's importance. So our more contribution is based on the mathematical formulation and discrete optimization for this angle for this problem. So in particular, we provide a strong mixed integer formulation for this maximum entropy sampling problem, and we derive better performance bound compared to existing result. So our performance bound, we didn't assume anything about the monotonsity and the submodularity or non-negativity assumption. So our bound is regardless of all these assumptions. Okay. So what kind of formulation we have derived? So this formulation is also quite interesting. We got this from a very new and a different angle. So you look at this covariance matrix. So we are trying to select a principal cell matrix of this covariance matrix. So this original formulation is very neat, but it's kind of not very useful to derive a nice mixed integer formulation. So to make this more desirable, so we consider the very generic Cholesky decomposition of the covariance matrix, because the covariance matrix is PSD, so we can always do that. And just for notation case, we use V to denote the columns of this matrix V. This is called Cholesky decomposition V. Okay. So another one is sometimes the matrix might be the rank maybe equal to D, and we have equal to S, but the X can be some singular. So the determinant of X might be equal to 0. So in this case, we define a new metric for this determinant called determinant S, which just is equal to product of S largest eigenvalues. Okay? So it's like this kind of form and this kind of form. And then we have, so it's a very simple determinant identity. So we can compute it. So we know the C equal to VV transpose, and the CSS can be equal to the VS, the subset of columns of V times transpose to self. Okay, but now we know this determinant equal to the product of largest of all the eigenvalues for this case. And then we know the VV transpose and the V transpose V, they have this similar non-trivial singular values, so non-trivial eigenvalues. So these identity follows. So whenever we see the VV transpose in this kind of form, this immediately we realize this will become the summation rank-on matrix. So using this summation rank-on matrix, then we are able to show that. So this when we have this one, so for each item or each column, we can define whether this column be chosen or not. Then we can arrive at this kind of mixed integer formulation where the X variable equal to 1 means the ith column is chosen, otherwise it's 0. So we end up with this kind of a mixed integer formulation. But so a little bit of misfortune that this formulation only, it's already a MIP now, but the object function is non-concave. So which means, if we want to solve this using branch cut, so it's very hard for us to derive a cut for this type of objective. So alternatively, we would like to derive a convex or concave envelope for this object function. So how can we do that? So we can do it using the high level idea is we can do it, we can convexify it using derive the convex conjugate of this function, this log determinant S function. So to end up with, we end up with this kind of very a little bit complicated gamma function, and this function has kind of have a sorting arguments, and it's a little bit complicated here. But the idea is we derive this based on the conjugate convex conjugate of original determinant log determinant S function. And it's worth mentioning this gamma S function has been found in this Nicholas paper, 2015 paper. That's a very interesting paper. So if you want to study this problem, this his paper should also be a very nice reference. Okay. So we prove this based on a different angle from Nicholas. We use the Lagrangian dual, which is just the conjugate. So to do that, we so we note that we introduce a positive semi-definite matrix variable like this summation of this one greater than S, and then we maximize the dot determinants of X because the monotonsity, so these two formations are equivalent to each other. So why we do that? Because of the determinant, to take derivative of log determinants is kind of easy to do that. And for so now next step is just relax using Lagrangian relaxation to relax this Lagrangian multipliers to relax this kind of inequality, and then we can then involve this convex conjugate. So I do hand waving here, but the idea is we relax this and with Lagrangian multipliers, and then we convexify it, the object function. So, and the nice part about this result is in fact, for any binary solutions, the gamma function, which is a concave function, and this log determinant, which is not concave function, they touch at each binary point. So which means this formulation, the original formulation, is the gamma S function is essentially exact if we enforce gamma X variable to be binary. So another one is also it's interesting is here is the gamma function is differentiable in the interior or relative interior of field region. So if X is if X is not equal to 1 or 0, so it's completely in the relative interior, then this gamma function is differentiable, and we can derive this gradient or subgradient in closed form. So then we can apply different different first order methods to solve the convex relaxation as a one star to branch cut method, for example. And we solve it because we want to use the continuous relaxation for results for our approximation algorithms. So we solve it, and it has 1 over t convergence rate of convergence, and this L is essentially the smoothness factor of this gamma function. And so we apply this Frank-Wolf algorithm because this Frank-Wolf always usually when it terminates, it's always give us a very sparse solution. So that's another way. Okay, so the solution is sparse, and we can generate for example, we can do run sampling algorithms even faster if we know that the output is sparse. So that's the formulation, and we also next we use our approximation algorithm to demonstrate that these kind of continuous relaxation bound is not only it's not only provide us a good bound, but also we are going to know how good this continuous relaxation bound is. So this is based on our first approximation algorithm. So so we use a different sampling approach than the literature. So we use the sampling approach based on the Mohit and my the 2018 paper. We use this kind of sampling scheme. So this scheme is so for when we solve the continuous relaxation, we take product of each components from the subset. For any subset, we take a product, and then we normalize with by sum of all the product together. So this kind of scheme is sampling scheme is quite useful for these type of models, and the sample procedure. So it also can be computed very efficiently by computing the coefficient of some polynomials. So we can compute this very fast in a very fast way. And the nice results about this continuous relaxation is about this sampling algorithm is we show this equal to the have some approximation bound here. This s times log this number. So which it looks like a little bit weird, this number. So I will illustrate it later as a Girard graph. So but the inner part of inside the log essentially equal to a constant. So, and we have approximation bound, we don't have ratio. The reason is because Z star, the optimal solution might be negative. The approximation bound doesn't make any sense. So we use approximation ratio doesn't make sense. So we use approximation bound instead of approximation ratio. So the proof idea is we have sampling algorithms and we take the expectation of the object function and evaluate it, use the majorization of eigenvalues and using the property of a determinant and its corresponding between determinant versus the eigenvalues, and then we are able to derive this bound. And this bound is improved using result. So it's currently the best known approximation bound for this type of algorithms. Okay. So another algorithm we use a lot, and essentially that's also the most powerful algorithms we can use for this type of problem is called local search algorithm. It's a very simple local search algorithms, and we can use it in many type of different problems if we have similar structure. So the local search algorithms, as many of you already know, so we given a subset of S, and these are we are currently chosen, and we have some nodes which are, some sensors are not chosen, for example. And then we swap this one of the chosen one with another one which are not chosen. And then we form a new solution, which is here. That's our new solution. So in this swap solution, what we do is we just plug in the solution to the original object function, and we check if this new solution gives us a better objective or not. If it's yes, then we accept this swap. Otherwise, we keep on doing until we cannot find any better solution. So a little bit more work, we can show this has this type of time complexity, but in practice, this algorithm works much better because we don't need too much iterations. The solution quality will improve a lot. So essentially, we don't need too many iterations to stop this procedure. So in practice, this algorithm works even better than the sampling algorithms. And also, it's worth mentioning that because we do comparison, so and it's also very interesting to use the Rincon update formula to compute this these two determinants, because for large scale problems, those determinants can be very difficult to compute, and it's very very expensive. So for this time sake, I will directly jump to the results. So we got also approximate ratio for the local search algorithm by construct a feasible solution to the dual problem of our convex relaxation model. And then we apply weak duality, and then we can find out some of those constants, which is essentially give us approximation bound. And you'll notice that this bound is essentially a little bit worse than the previous one because we have log S here, and the previous one, this log term essentially become a constant. So we can also draw this curve. You know, the local search bound is slightly worse because we never use any Wong style for local search. So we start with an arbitrary actual solution. So that might be one reason local search bound, theoretical local search bound is a little bit worse. And our sampling bound is better than the existing one. So okay, for the sake of time, I will directly jump to the numerical study. So we use first of all, we use the numerical instance from Professor Kurt in our state, and we see that those time for even n equal to 124 to solve this problem using a exact method takes almost several days to compute this ones. And our continualization bound, using Frank Wolf can be solved very relatively efficiently. And the sampling algorithms. And the sampling algorithms is based on the continualization. So the time is we use the sampling procedure and the continualization together. So it's a little bit longer than, seems it's much longer than local search. So you can see that, so local search algorithms, so give us a so the gap is almost equal to 0. So that's the one powerful part of this algorithm. So, and its running time is really short. So as I explained, because we don't need too many iterations to terminate the local search procedure, so essentially in practice works very well. So we try a larger scale case. This is from Chanton's data set. They use this for sparse PCA, but now we can use this because we have similar structure. So they also use covariance matrix. So we test on their data set and we see that local search still works very well. But you can see that the continualization or sampling algorithm takes much longer time now. The reason is the computing the gradients is time consuming. So it takes more time to compute the gradients in quart and run the subgradient or the gradient Frank-Wolf method. But the local search still it's very, very fast. And finally, we try this in the polished data set for PMU sensor placement. We have more than 2,000 buses. And if you want to select 300 sensors, so our local search algorithm still takes 5 minutes. Less than 5 minutes, and our gap is 0.2. So we just compute the gap directly from continualization bound and the local search bound. So for this type of problem, continualization bound is already give us a very nice bound. So the open question here is how can we close the gap using branch cut? So we tried and they're not successful because it takes too much time to close gap. So the gap is almost equal to 0.2 for a long time, and we are not able to close it within an hour. So I think this is an open question. If you're interested, this is a good way to try. All right, so before I run out of time, so in this talk, we study maximum entropy sampling problem, and we see that by exploring the problem structure, we can derive a very better approximation continualization bound. And based on this continualization results, we can analyze local search algorithms, and also the rank 1 update is really powerful. Can reduce the computational time a lot, and this method can be extended to other interesting problems. For example, if we have different object function here, and if you are interested, our paper is already online. Yeah, so I will stop. Thank you.
Thank you very much. That was a really nice talk. I actually do have questions, and I think other people might as well, but is it okay if we keep the questions for the question and answer session afterwards in the private breakout rooms rather than doing it right now? Or yeah, I think that might be best, just so we can let the people who want to leave at 3 p.m. Leave at 3 p.m. So yeah, thank you very much. That was a really great talk. Yes, and please stick around for after the talk. There will be a time to ask questions for Weijun in the special room. Okay, so sure. 1 second. I'm going to stop the recording for this one and start for the next talk now.